Welcome to a lesson with Dr. Powell. In this video, we will look at how to build a Mobius matrix for Poset. So let's get started. Let's take a look. If we have a Poset structure as follows, we can think about this structure as giving some kind of structure to an ordered tuple, such where I have like 4 things here in this tuple, and I have these 4 nodes, but they have this structure of arrows. So this position represents the top node, this one represents that node, and so forth. So an ordered tuple of numbers can be thought of as in a Poset picture. And now, of course, that ordering depends on some choice here, but dependent upon that choice, we're going to be able to have something called a Mobius matrix for a structured Poset. Okay, so we're going to be thinking about every node as retaining 2 pieces of information. One as being, see these question marks? These question marks are information about things to add. So we're going to be adding some things up in such a way, and that's the question marks, such that the sum of everything up until that node is going to be something. So in this particular case, a question is being asked. I want the total sum up to a point, up to the bottom vertex, to be 1. I want the sum of all the nodes up to and including this vertex right here. So that would be like this one and this one. This one does not lie below that one, and neither does this one. So the sum of these 2 nodes I want to be 0. The sum of all nodes up until this point, including this point, of all of these up here, I want this to be 0. Total sum of 0. I want a total sum of 0 right here up to this point of this node and everything below it, which means just these 2. So it's kind of like I have an ordered tuple, 0, 0, 0, 1, and according to the way that I'm prescribing this, with the 1 being at the bottom, I'm going to be thinking about this as being like a standard basis vector, thinking of a vector space here, thinking of this as being a vector. With a 1 at this end, that would make E4 as a standard basis vector. This one right here we can think of as being E1. Okay, so E4. So it's kind of like saying E4 gives us the sums here. And then the question is, what are the nodes, the question marks, such that we answer those sum questions that we were just discussing? Well, here they are. Notice that if these question marks are filled out with a -1, and let's actually write this out. So let's suppose the sum right here is, so the sum up to this point is a, so really to fill in this question mark, a 1 would do. To this point, a -1, a -1, and a 1. And notice the sum up to this point, 1 and -1 will be 0. Sum up to this point, 1 and -1 will be 0. And up here, we have 1, -1, -1, 1, that's a 0. And here, just to the bottom, a 1. So these numbers right here answer those questions. So it's kind of like this is telling us sums. And I'm going to call these nodes the answers to the questions right there to fill up, to find cumulative. So the cumulative sum up to a certain vertex is given by this node structure right here. So it's kind of like a question we're asking, how to move from sums to nodes. And actually, such a question, in general, is a linear transformation. We're going to figure out the destinations of all the standard basis vectors from E1 through E4 for this Poset. And notice that this one for E3, so E3 right here, these are sums, these will be nodes. answers the questions. And similar we have for E2 and E1. You can go ahead and check those and see how that works. Now, if we know for a linear transformation the destinations of E1, E2, E3, E4 here, and that's a standard, that's a basis for the domain, we actually know the destination of via matrix multiplication for anything in the domain. Meaning if I give you any sums, cumulative sums up to any up to vertices, I'll be able to tell you the nodes via a linear transformation. So these right here, the images of E1, E2, E3, E4, I actually just computed in the diagrams previously. On this up here for E4 and then here for E3, E2, E1. And ordered, we can write out these. And then if we're thinking of a column interpretation for a linear transformation, we can simply write these down. The image of E1, the image of, so we have the image of E1, the image of E2, of E3, E4, like that. Okay, so if I gave you a different set of sums, 10, 5, 2, 1, we can fill out these question marks by running a simple matrix computation. This matrix times this input vector, which really just represents the sums right here, 10, 2, 5, 1, in that order, and we run this computation, we'll get this as an output, and this right here corresponds to the sums that we want. So writing this out, notice, okay, so notice right here in this computation 10 corresponds to the 4. So 4 to answer that question, the 1 with the 2, the 4 with the 5, and the 1 with the 1. The sum of 1 and 4 up to this point is 5, 1 and 1 is 2, 1, 1, 4, 4. Hey, that gives us 10 at the top. All right, so we can answer these cumulative, node questions for a particular sequence of, or set of cumulative sums via a computation like that. Okay, so this matrix right here that we just found for this particular Poset structure, of course, depended on the order of how we wanted to order things. It looks like the top is kind of like came first, at least in this particular case. This node came second, so the left node came second, then it looks like the right node came next, and then the bottom node came last. I mean, we could have ordered this differently, and we would have gotten a different matrix. So the Mobius matrix really depends on how we've ordered the vertices. So, but according to this ordering of vertices, we have the Mobius matrix for the Poset. Okay, so let's take a look. Okay, and if we like, we can actually see this, the nodes right here. We have 1, 1, 4, 4 written out like that. Let's take a look at a different Poset. And here I actually give you the nodes. In fact, I even give you the matrix. And I give you the sums. All right, so we have right here the sums and the nodes that answered the questions. And this is the linear transformation, which, as a function, inputs the sums and outputs the nodes. How do we get it? By finding the destination of E1, E2, E3, E4, in this case E5, according to a particular ordering. What ordering did we use? Maybe we can investigate that. Well, it looks like, see this 1, -1? In my mind, I'm thinking, well, what if, so if this represents the bottom right here, the bottom node, then I can kind of think, okay, 1, -1, that would be a solution for E1 if this was like if there was a 1 here and zeros everywhere else for a zeros everywhere else for the sums. So it looks like this would be like the destination of E1 to me. For E2, I would think, okay, well, let's see. Let's erase those and think for a minute. So E2 has a structure, for starters, like assuming that it's going the order I'm thinking, maybe 0, 1, and zeros everywhere else. So if we're going like this, what sums would actually get us this? Well, a 1 here, and or so nodes, question marks. So if these are the sums, and maybe what I'll do is I'll think, maybe I'll draw lines like this, okay, for the question marks. 0, here a 1, here a -1, here a -1, and here a 0. And notice I think that works because the cumulative sum up to this point of things above the line that I drew, 1, -1 is 0. 1, -1 is 0 to that point. Up to this point it's just a 1. 0, nothing's below this one, and 0, nothing's below that one. I think that works well. So this would be the second thing in the ordering. Assuming it's this one is next, and let's think about that. Maybe, let's see, if this is there's two things above it, and both of those things would have to be -1s in the question marks, so that looks like it's good. And then these two just correspond to things on the top. Well, actually, that was silly of me, because really, the ordering can be seen right here in the sums. So, you notice the sum of 2 is right there. The sum of 4 is right here. And sum of 1 is right there. Sum of 13 is over here. And the sum of 17 is up here. So looking at that, putting in these sums into this matrix will output the respective nodes. And all we needed to do to get this matrix was just need to know the images of E1, E2, E3, E4, and E5. Thanks for watching.